session in the conference because the two looks like two things happening at the same time. It's a concurrency session. You can't just make this stuff up. We've got three great talks. The first one, model checking for weakly consistent libraries, and this is Michalis.
Okay. So hi everyone. Thank you for being here. This is joint work with Azelia Rad and Vector Vafiadis, and has to do with verification of concurrent programs under weak memory models. So how do we verify a concurrent program to begin with? Well, one popular way of doing so is with stateless model checking. And stateless model checking basically says that given a concurrent program, we can simply enumerate all of its executions, but without explicitly storing the visited states, where states here are the executions that we've already seen. Now, stateless model checking is associated with two major challenges. The first challenge is the state space explosion that's inherent to concurrency, and basically means that we have a very large state space to begin with. You can imagine that if we have a sequentially consistent program and we want to enumerate all of its interleavings, then this number is going to be exponential. And the second challenge is the weak memory models employed by modern microprocessors that introduce new behaviors that we need to take into account. So I'm going to try and briefly summarize what has been done about these two challenges and what's left to be done. Okay, so as far as the state space explosion is concerned, what we do to tackle this problem is equivalence partitioning. So we take the whole state space, we partition it into some equivalence classes, and then instead of exploring all executions, we try to explore one execution per equivalence class. And this is usually done with partial deduction. So let's see an example of this. If we have this program where x and y are necessarily 0, and the first thread is writing 1 to x, the second thread is writing 2 to x, and the third thread is writing 42 to y, how many executions does this program have? And I'm assuming a setting of sequential consistency for all the examples unless mentioned otherwise. Now, a stateless model checker would say that we have to explore 6 executions for this program because there are 3 instructions that can be interleaved in 3 factorial ways, so we have to explore 6 interleavings. Now, if we combine stateless model checking with a classic partial deduction algorithm, then this algorithm would only explore 2 executions. And it would do so because it would notice that the third thread is independent with the other 2. It's writing a different memory location. So there's only one race between the first 2 threads, and it would explore one interleaving where the first thread is executed before the second, and then another one where the second thread is executed before the first. Now, this mode there stands for modification order, and basically means that this classic partial deduction algorithm maintains a total ordering of the writes of each memory location. This is taken into account when we do this equivalence partitioning, and it is why the 2 writes to x are considered racy. Now, the reason I'm mentioning this is because there are some even smarter partial deduction algorithms that would only explore 1 execution for this program. And they would do so because they would notice that there's no one actually reading from any of these writes. So there's no point in exploring more than 1 execution. And this PRF there means exactly that this algorithm only distinguishes executions based on PO, program order, and RF, so reads from. So as far as the state space explosion is concerned, there has been done quite a few work, and this is good news. But then when it comes to weak memory, while there have been partial deduction techniques that handle weak memory models, all these techniques are memory model specific, and they cannot be extended to handle different memory models than the ones they were designed for. Now, there is one tool called HERD that can handle different memory models, but HERD is not a model checker, and it doesn't scale to big programs. So now this raises the question of why isn't there a generic partial deduction technique that can handle different memory models, and more specifically, what memory model properties are sufficient for us to have an efficient stateless model checking algorithm? And this is where we come in. So what we did is that we investigated and we present sufficient properties for efficient stateless model checking, and then we developed GenMC, a stateless model checking procedure that is parametric in the choice of the memory model. So as long as you have a memory model that satisfies a few basic assumptions that we have in the paper and that I'm going to present in this talk, then you can use GenMC to verify programs under any such memory model. And moreover, we've proven that GenMC is sound, meaning that it explores no false positives, that it is complete, meaning that it explores all executions, that it is optimal, meaning that it doesn't explore the same execution twice, and that it is efficient, meaning that it uses this coarse PRF equivalence partition that I mentioned before. And we've actually shown that it is efficient by implementing it into a tool, comparing with other state-of-the-art model checkers, and in many cases, GenMC is able to explore exponentially fewer executions than other model checkers. Now, the best part about it, however, is that it can also be used to verify programs under memory models that incorporate higher-level libraries as their primitives, for example, lock and unlock operations. So in the rest of the talk, I'm going to try and present the assumptions that we have with the memory model and how we arrive at these assumptions, and then going to conclude with some results. Right, so our starting goal is very simple. What we want to do is enumerate all consistent execution graphs of a program P for any memory model. Now, how do these execution graphs look like? Well, if we have a program like this, where the first thread is writing 1 to x, the second thread is reading from x, and the third thread is writing 2 to x, then there are 3 executions for this program, depending on the value that this read reads, that can be depicted by these 3 graphs. Now, in these graphs, the nodes correspond to instructions of the program. For example, this means write to x the value 1. The black edges are PO edges, so program order. They connect the events of the same thread. And the green edges are reads from edges, RF, which show where a particular read is reading from. So in the first execution, this read is reading 0, the initial value. In the second execution, this read is reading 1 from the first thread. In the third execution, the read is reading 2. And so what we want to do is systematically enumerate such graphs for a given program. And of course, the question is how to do that, how to systematically enumerate all graphs of a given program. Now, it turns out that this is not trivial. And to see this, I have this example where the first thread is reading from y and writing the value read to x, and the second thread is reading from x and writing the value read to y. And the question is, can the reads of this program read 42? And note that this value 42 doesn't even appear in this program. This is known as an out-of-thin-air behavior. But the point is that if we have no assumption on the memory model, the answer is yes, perhaps surprisingly, because we can have graphs like this, where, for example, we assume that both writes read 42, and then this read over there reads 42 from the second thread. This feeds this write of the first thread, which is read from the read of the second thread, that feeds this value that started this whole thing. So we have this PRF cycle there. And again, if this is not disallowed by the memory model, then this is a consistent execution. And in fact, the reads cannot only read 42, but they can read 43, 44, 45, whatever, and the number of executions can be infinite, even though this is a finite program that has no loops whatsoever. And of course, if the number of executions is infinite, then we cannot systematically enumerate them. And this leads us to our first assumption on the memory model. And we demand exactly that we do not want such cycles, such out-of-thin-air behaviors, so we just say that we want PO union F to be acyclic. So that's good. And if we have that, we can systematically enumerate all executions. And the question that we have to answer right now is how to do that. Now, the naive way would be to just create all possible graphs and then check for consistency according to the memory model. But of course, this is too wasteful because we have to generate all graphs and then check for consistency and so on. So we generate too many inconsistent graphs. And what we would like to do instead, how we would like our algorithm to work, would be to check for consistency at each step. And what does this mean is that if we have the same program as before, with the same 3 graphs, the same 3 executions, we would like to be able to generate each of these graphs incrementally, starting from the empty graph, then add events one by one, and then arrive at each execution, and only make consistent options so we don't have to consider any inconsistent graphs and keep inconsistent graphs around. For example, we would like to generate execution number 2 somewhat like this. Start from the empty graph, then maybe at the write of the first thread, then maybe the read of the second thread, reading from that write, and then add the write of the third thread. This is how a real CPU could have generated that execution. Now, in order to be able to do that, in order to be able to incrementally generate the graphs, we need another assumption from the memory model. And we need to know exactly that each execution can be obtained following some linear extension of PO union F. Now, what this linear extension of PO union F says, this says that before you add each event in your graph, you should have added its predecessor in the same thread. And if you're about to add a read, you should have also added the place where it's reading from. Now, if we have that, then we know that that there is some way that we can generate each graph incrementally, but this doesn't say which is that way. But fortunately, all major memory models offer something even stronger. They say that it doesn't matter which extension of PRF you take because any will do. and this can be rephrased as prefix closeness. So prefix closeness says that you can generate each graph incrementally by taking any linear extension of P or U or F, or equivalently that if you have a consistent graph and you take any P or F prefix, then this will also be consistent. And this is good news because with these two assumptions, we know that we can generate all graphs incrementally, but there is still one problem. And the problem is that this prefix closeness assumes that you know the graph that you want to arrive at beforehand. But in our case, we don't because we want to generate these graphs, right? And the algorithm does so by using a fixed construction order. And although I won't have time to go through the algorithm, I'm going to roughly show you how it works. So you have the same program as before, and the algorithm basically starts from an empty graph and uses a fixed order. For example, suppose that it adds the events from left to right. So it will just add this right. It will add a read where this is reading from this right, for example. It will add the other right of the third thread. It arrives at one execution. Then it notices that, OK, that read could have also read from there. It arrives at another execution. Then it says, OK, when this read was first added, it could have also read 0. So then it proceeds again. It adds some events. It arrives at the third execution. This is roughly how it works. But the thing is that we need to know that this procedure that generated all graphs with a fixed order will not get stuck. And this brings us to our third assumption of the memory model. And we need to know that the memory model is extensible. Or in other words, that when you're adding a read in a graph, there will be a place for it to read from, or equivalently, that the operational semantics of your memory model will not get stuck. So these are our three assumptions. The first one says you can systematically enumerate all graphs. The second one says you can incrementally generate each graph by following any linear extension of P or U or F. And then the third one says that, OK, we can also generate all graphs using a fixed order. And from these three assumptions, the last two are basically things that all sensible memory models offer, including memory models like SC, TSO, PSO, and RC11. But PRF acyclicity is not offered by, for example, Power and ARM, although these memory models have a similar condition to route sets behaviors, they track dependencies, and so on. But the idea is that if you have a memory model that satisfies these three assumptions, then you can use GenMC to verify programs under this memory model, even programs like this, where instead of reads and writes, you have locks and unlocks operations. And then if you assign read semantics to locks, for example, and write semantics to unlocks, then the executions of this program can be viewed like this, where in this execution, the first thread acquires the lock first, and then the second thread follows, and so on, the second execution. So moving on to some results, there are three things that I would like to point out. So we implemented this algorithm into a tool called GenMC for C programs. And we implemented it for the RC11 memory model, which is a repaired version of the C11 memory model. We implemented the tool both under this MO equivalence partitioning and under this PRF equivalence partitioning that I mentioned in the beginning. We compared against RCMC that also works for the RC11 memory model under MO. And we also compared against NIDHUG that works for sequential consistency and sequential consistency with observers. That's a coarser partitioning than SC, but not as coarse as PRF. Now, this Lamport benchmark is an implementation of a lock by Leslie Lamport, and then there are a bunch of threads, the numbers in the parentheses, that use this implementation and use this lock to manipulate some shared variables. Now, the first thing to notice here is that GenMC for 3 threads is faster than all the other tools due to this coarser equivalence partitioning. But another thing to notice is that when we go from 2 to 3 threads or from 3 to 4 threads, for example, for 4 threads, no tool manages to terminate within 2 days. So the state space of this program increases rapidly. Now, what we can do about it, however, is that if someone, for example, is not interested in verifying the implementation of the lock, and someone is only interested in verifying how this lock is used, then we can use GenMC to abstract over the implementation, treat lock and unlock operations as primitives of the memory model, and then GenMC can finish instantly for 4 or even more threads. Now, of course, this is not the same benchmark as before because you're no longer verifying the implementation of the lock, but this is a nice example of compositional verification and how a tool like GenMC can be used. Now, the second thing that I would like to show you is that GenMC is faster for 3 threads under this PRF equivalence partitioning, and this is not a coincidence. And this is because this PRF equivalence partitioning is exponentially coarser than this MO equivalence partitioning. So these are 4 benchmarks, In the y-axis, we have the number of executions. In the x-axis, we have the number of threads. And this axis is logarithmic. And as you can see, this PRF equivalence partitioning explores exponentially less executions in all these benchmarks. And the third thing that I would like to show you is that a comparison between the MO variant and the PRF variant of GenMC in 200 different benchmarks. And as you can see in this scatter diagram, there are a lot of cases where the PRF version is faster or exponentially faster than the MO version, even in terms of time, and only one case where the MO version is a bit faster than the PRF version of GenMC. Now we have more things in the paper. In the paper, you can find a detailed description of the algorithm, a formalization of the assumptions that we have in the memory model, as well as more benchmarks and evaluation. To conclude, I've presented a sound, complete, and optimal stateless model checking procedure for memory models that satisfy a few basic assumptions. We've shown that GenMC can be exponentially faster than existing tools since it explores exponentially fewer executions in a lot of cases. And we've also made GenMC available on GitHub, and we would very much like bug reports or feedback on it. Now, as future work, we would like to see if we can further relax the assumptions that we have in the memory model. Thank you.
All right, we have some time for questions. Please come to the microphone if you have a question.
Hi, I'm Jens Pausberg. Did you try this for Java?
No. This is for C.
Okay. Let me encourage you to try Java. So Java is a language where this assumption number one about PO union IF is acyclic is built into the memory model.
Yes.
And so
we would like to try it, but this requires some effort on the implementation part. So this is why we haven't done it yet. But in principle, the algorithm could be applied to Java.
I wanted to ask about the extensible piece. It's a little counterintuitive that this is important because if I'm trying to enumerate all states, getting stuck only seems helpful, right? It also seems like you should be able to encode it away. Like instead of getting stuck, you move to some special sentinel state from which you don't escape or something, right?
But the point with the extensibility is that we do not want to get stuck because if we get stuck, we may miss some execution. So if you're adding some events and then you get stuck, then you may miss some execution that you could have generated if you had followed, for example, a different ordering.
I see. Other questions? All right, let's thank our speaker.